that page, you have two independent things happening. First, we're going to draw a graph through the blue point that we're given, okay? So the way in which you do that is this. So take a look at this first one, right? The blue dot is over here, right? Do you see how that is between, you know, this and this, yeah? And it's between this and this. So it's literally like you're in the ocean and you're following a current, right? So you are going to follow that current here in between those two. Do you see that? So here it's in between this and this, right? You're going in between. That's the best way to do it. Okay. Here, again, the blue dot is over there. And let's see, you know, it's between like this one and this one, this one and this one, right? Literally, you're going to stay inside that current. That's more true than you would imagine. Remember, this is the sort of thing that could be, like, it could model, let's say, an electric field or a magnetic field, right? And it's like, it's actually how those lines will go, right? So that makes it a little bit more manageable now, right? Let's do 14, right? So it's between here, and here it's between like these two. Do you see how when you follow those guides, it's like bumpers, right? Right? Like for bowling and stuff, like there is no other way now to draw that. Do you see that? Does that make it a little bit better? Yeah? Okay. Now, let's talk about the other situation. The other situation is to match each of these with the graphs. Okay, and to do that, we need to look for trends. So the way I would do this page is I would start with the row of functions. And for me, and just in general too, the easiest ones to do are the ones with a variable in the denominator. So E and F are the easiest ones to get rid of, right? Because take a look at what E says. E says when x is 0, the derivative is undefined. Undefined derivative means infinite slope. So like the slope has to be a vertical line. So here, when x is 0, that's along the y-axis, correct? So look at all your graphs to see which one along the y-axis do you have straight up a vertical slope. C doesn't have a vertical slope along the y-axis. Neither, 11 doesn't, 13 doesn't, 14 doesn't. The only one that has, you know, a clearly a vertical slope along the y-axis is number 12, because as you go closer and closer, these slopes are just going to be vertical lines, right? So that's why this one is E, okay? So now we did this one and this one's out. Now, F is a similar situation, except now slope is 0 when y is 0. Y is 0 is the x-axis. I'm sorry, slope is undefined. Undefined slope along x-axis. And this is how even the professionals would do it, okay? So if you look along the x-axis, which one has definitively vertical slopes along the x-axis? Not 11, because look, it's curving at some points, right? Along the x-axis. 13, not 13 either, because along the x-axis, look, there is some curvature. Not 14 either. 15, definitely not, because it's not vertical slopes here. But look at 16. The whole time along the x-axis, the slopes are vertical, right? So that's the one. Okay, that's the one with vertical slope along the x-axis. So now this one is out too, and so is F. Okay, next, the other two that are now easy are A and B. right? What does A and B say? A says the slope is just dependent on x. So that means for positive x values, you're always going to have positive slope. For negative x values, you're always going to have negative slope. There is a clear division, right? Negative slope, zero slope, positive slope as you go left to right. So which one, as you go from left to right, you only have negative slopes on the right and only positive ones on the left? Well, that's only A. A is the only one where there's a clear division. Zero along here, negative to the left, positive to the right. So that's A, and that's out as well. B is similar, but with Y. Okay? Positive slope along positive Y, negative slope along negative Y. So, and then there is zero slope here, right? Zero. So which one does that follow? Not this one, because it's all a mix. Not that one. This one. Look at this. Positive slopes, zero slope, negative slopes. Right? So it's 15. Positive slopes here, negative slopes here, and zero slope along the axis. So that one is out too. And so is this one. Okay, the other ones are C and D. The best way for these is, again, to see a trend. The way I would look at C is, it's x minus y. So when y is bigger than x, the slope is negative, right? Does that make sense? Whenever y is bigger than x, the slope is negative. So how are we going to do this? Be very, very systematic. Pick one area. So let's see for this one. Pick this point here, x equals whatever, 1. As you go higher and higher, as the y gets bigger and bigger than x, the slope is getting negative, right? So that's the one, that's C. The other one, D, for bigger x, you have negative slope, right? So look at this one. Pick a y value. The bigger the x's get, the more negative the slope gets. So do you see how it's it's a trend sort of situation, yeah? And again, this is how even the professionals do it, okay? All right. Okay. So let's move on to the notes. Yes. No. Okay. So we left off, right, in the previous episode, doing, right? Yeah. Previously in chapter 7, we were doing this, solving differential equations. Okay? We're going to do more. We're going to put it in some context as well. Okay? So let's do it. Okay? Here we go. We're going to go back to exponential growth and decay. And you've had a lesson called exponential growth and decay every single year since Algebra 2, right? Mm-hmm. Yep. And now this is almost the grand finale, almost, in calculus. Okay. So, when you have a differential equation in the form of this, where you have dy dx is f of y times g of x, we call it a separable equation. Okay. What does it mean? You can separate the variables like this. So for example, if you have dy dx is equal to some function with a y in there times another function with an x in there. Okay. What you can do is you can divide both sides by f of y, right? So you get 1 over f of y, and then is equal to just g of x over there, right? But what you could also do is bring the dx over to that side. So here you just have dy equals dx. Yeah? So what you've done now is you have separated all of the y's on one side, everything with the x's on the other side. This is why this is called a separable equation. And what we've done is called separation of variables. Okay? So that's what we're going to do now. We're going to use separation of variables to solve this initial value problem. And then we have to indicate the domain over which the solution is valid. So same sort of situation. Here, you see how you have x over y on the right-hand side. You didn't have that before. It was just in terms of x in yesterday's notes or the previous day's notes. So what we're going to do here is multiply both sides by y. So you get y dy dx is equal to x. Take the dx over to that side, so you have y dy is equal to x dx. Now you can actually integrate both sides. So we're going to get on the right-hand side, on the left-hand side, y squared over 2 equal to, on the right-hand side, x squared over 2 plus c. Yes? Now, we have initial conditions. X is 2, y is 1. So when y is 1, we get 1 over 2 is equal to 4 over 2 plus c. So what's c equal to? Negative 3 over 2. Now what I'm going to do is I'm going to take the c and plug it back, not into there, into here. All right? So I'm going to get y squared over 2 is equal to x squared over 2 minus 3 over 2. Yeah. Multiply through by 2, so y squared is x squared minus 3. Y, when you take a square root, is plus or minus the square root of x squared minus 3. But now we have a little bit of a situation because we have two solutions for y. So the question is, are both of them okay, or are we just supposed to choose one of them? Because our solution has to be something that satisfies the initial condition. When x is 2, y should only be positive 1, not negative 1. So the way it stands now, okay, at x equals 2, you can get two answers. You can get y equals positive 1 or y equals negative 1, but you can only get one of them, right? So which of the radicals are we going to choose? The positive one. Okay? So that's the solution. Next, what I want to do is I want to identify the domain. For the domain, I know that x squared minus 3 has to be greater than or equal to 0. Okay, now, if this was a linear term, like x minus 4, you would just say, x is greater than 4 and be done with it. But since it's a non-linear quadratic term, we have to do a sign chart. And we did this a little bit in pre-calc, but I know we forget. So where is x equal to 0 here? Plus or minus root 3, correct? So the process, and this is algebra 2/pre-calc. The process is you make a sign chart. Negative root 3, positive root 3. Now, you have to plug numbers from each of the region into x squared minus 3 to see which region will give you positive values, right? So when I plug in a 0, I get negative. And then here gives me positive and positive. So my domain is negative infinity to negative root 3. Right, that's why I'm not taking that. No, what? No, I'm looking at the radicand. Yeah. Okay? So that's the domain. We're cool? Can you sit properly? Sorry, thank you. All right, are we cool? Okay. So next, take a look at this one. Again, we got to do some separation of variables. So dy dx is xy squared. In order to be able to separate them, you have to multiply this out. So dy dx is x squared y squared. So now I can bring the y squared over to the other side. So it'll be 1 over y squared dy is equal to x squared dx. Okay? Now, integrate, integrate. So basically what I have here is y to the minus 2 dy is equal to x squared dx. Same as what we were doing before from the worksheet, right? So this will be y to the minus 1, which is 1 over y with a negative. Don't forget to divide by that negative. Equals x cubed over 3 plus c. Now, plug in the initial condition. Y is 1 means negative 1 equals x is 1/3 plus c. C is negative 4 over 3. Okay, so plug it back in here. Negative 1 over y is x cubed over 3 minus 4 over 3. And here, students want to do all sorts of acrobatics to solve for y. But the easiest way is this. This is negative 1 over y equals, since you have the same denominator, why don't we just write it like that? Yeah? Now, you have 1 over y, you want to solve it for y. Flipping one equation means you can flip the other side as well. So negative y is equal to 3 over x cubed minus 4. So y is negative 3 over x cubed minus 4. Okay. As far as domain is concerned, all is good except when the denominator is 0. So basically all you have to say for domain is x cannot equal cube root of 4, and that's good enough. Okay? Okay. Now, okay. All right, so let's talk about exponential growth and decay. If you have a situation where y changes at a rate proportional to the amount present, right? That means, okay, let's talk about proportions for a minute. You do this like everywhere, math, science, but let's remind ourselves, right? If two things are proportional to each other, so suppose x is proportional to y. If I say x is proportional to y, how do I write that? X is proportional to y, it's k times y, right? Because if you divide, x over y will be a constant always. You see it in gas laws, right? PV equals nRT, right? Pressure is proportional to temperature, right? The temperature goes up, the pressure goes up. So how does that look? P is equal to, well, NT or KT, right? Right? There's a constant, right? So, so that's how, proportionality works. So if I said, something is proportional to whatever, then it's, A is K times the new constant. So here, if the rate of something is proportional to the amount present, then the rate is proportional to the amount present. The rate of change of y is proportional to how much y there is. That's how we write it. dy dt is equal to k times y. That should become like very familiar to you, okay? And if we call y naught the initial y at t equals 0, this is a differential equation. When you solve it, you should get that. Now, have you seen that formula before?
Yes.
It's like the formula. Well, guess what? All it is a solution of that differential equation. Okay? And then, so K is the constant of, it's the growth constant. If it's growth, then K is positive. And if it's decay, then K is the decay constant, and it turns out to be negative. Okay? Now, bankers have taken that formula, which is just a solution to a differential equation, that bankers have taken it, and then, they have modified it to their own sort of like terminology. So we get A equals PE to the RT, right? Which means if interest is added continuously at a rate proportional to the amount in the account, right? Amount goes up, rate, right? Like it's always like a proportional rate, right? The same, like 5%, 5%, 5%. Then here is the balance, right? A is the balance in the account. The rate of change of that is R times A, is proportional to the amount present. Okay? And when you solve it, if you call it, let's say, if the initial amount is A naught, then the solution will look like this. If you call the initial amount P, then it would look like this, right? It's just, like the same sort of thing. Yeah.
So when you say the rate is proportional to the amount present, no matter how big the amount present is, it's always the same.
Right, because, yes, because you're always being paid like 5%. Yeah. So you always get, like I said, 5%, 5%, 5%. So it's proportional. But now, let's really see if this is true. Okay, let's see how it is that this happens. So what's my equation? It's dy dt is equal to ky. Yeah? We're going to do separation of variables here. So dy over y is equal to k dt. We're separating. Bring the y over, bring the dt over there. We're cool with this part? Okay. Integrate, integrate. What's the integral of dy over y? Or 1 over y? ln of y is equal to, k is a constant, and when you integrate, you'll have k times t plus c. Right? So suppose this was like the integral of 5. When you integrate, you'll get 5t plus c, right? Okay. Now I need to solve this for y. How am I going to solve it for y? The e to the power of everything, remember? So e to the ln of y is equal to e to the kt plus c. What's e to the ln of y? Just y. Now, e to the kt plus c, right? So if I have, for example, a squared times a to the x, how do I write that? A to the power of 2 plus x, right? You add, when you're multiplying the powers, you add the exponents. But if you were given this, would you be able to go that way? Yeah. And that's what we're given here. We're given e to the kt plus c. We can go the other way, right? Can I rewrite this as e to the kt times e to the c? Why not? Okay, but, so this is y equals e to the kt. So c is a constant, right? And e is 2.7. So 2.7 to a constant is what kind of number? Still a constant, right? So can I just write this whole thing as like a c? Because all it is a constant. So can I now write it like this? C e to the kt? It's getting there. It's getting there. Yep. But what do we know? We know that at t equals 0, y is y naught. That's the initial amount, right? So at t equals 0, y equals y naught. So y is y naught equals c e to the k times 0. Plug in the initial condition. y naught is equal to c e to the 0, which is just c. So now, plug it back to here. Yep, y equals y naught e to the kt. That's where it comes from, right? Y equals y naught e to the kt. So, you are given that formula in Algebra 2, and you're like, oh, y equals, but you don't understand, like, you don't know where it comes from. You cannot appreciate it, and it's so sad because, I teach Algebra 2, and I tell them, and, everybody likes using it, but, like, it's so sad because you can't understand the full beauty of it until you can, like, see it like this, right? Like, everything that you use and you take for granted, all of those equations and formulas, they come from a beautiful place like this, right? Everything. Like, it didn't just fall into a textbook somewhere, Like, it wasn't like somebody woke up one day, opened up their journal, and there it was, like, magic. No, like, somebody brought it to us. So, that's important. Okay, so now that we did it one time, we don't have to do it every single time. Okay, which means, take a look at this. Population y grows according to the equation dy dt is equal to ky, where k is a constant and t is measured in years. The population doubles every 10 years. What is the value of k? So, we know that dy dt is equal to ky. That immediately, so here we go, dy dt is equal to k times y. That immediately tells me the solution to this is y equals y naught e to the kt. Now that we've derived it once, we have the rights, we have the credit to use it every single time. Okay? So, it says here the population doubles every 10 years. So, if initially the population was y naught, 10 years later, how much is the population? 2y naught. So 2y naught is equal to y naught e to the k times 10. 10 years. So at 10 years, y is 2y naught. Solving. Get rid of the y naught. 2 is equal to e to the 10k. ln of 2 is equal to ln of e to the 10k. So ln of 2 is equal to 10k. So what's k? Right, ln of 2 over 10. And if this is a non-calculator, like a multiple choice, this could easily be a multiple choice question. Then, you'll probably see it as ln of 2 over 10 in the answer choices. Or we can round this to 0.0693. Okay? Huh? No, with a calculator. Okay? I mean, we all know ln of 2 is 6.93, right? Sorry, 0.693, and then when you divide by 10. Huh? Okay. Okay. Yeah. So, a puppy weighs 2 pounds at birth and 3.5 pounds 2 months later. Okay? So, if the weight of the puppy during the first 6 months is increasing at a rate proportional to its weight, that's the magic phrase, then how much will the puppy weigh when it is 3 months old? Okay? Huh? Right. The weight is increasing, so the rate of the change of the weight is proportional to how much it currently weighs. Yeah? Yeah. So, we're going to use W for weight. So that highlighted phrase says the rate of change of the weight is equal to K times W. It's proportional to its weight. Okay? that immediately tells me that the solution to this is W equals W naught e to the kt. Do you see how it works? Okay, so to do this, we first have to find k. Okay, so a puppy weighs 2.0 pounds at birth. That means when t is 0, W is 2.0, which also means this is W naught. 3.5 pounds 2 months later means when t is 2, W is 3.5. So that's W naught. So let's go ahead and put those in here. W equals W naught e to the kt. Final W is 3.5. Initial is 2.0. E to the k times t is 2 months. You see how I keep track of my sig figs here and it differentiates the two 2's? Yeah? So here, you have 3.5 divided by 2, e to the 2k. Taking the ln of both sides, I have ln of 3.5 over 2 equal to 2k. So k is all this, ln of 3.5 over 2 divided by 2. And when you put it in your calculator, it's 0.2798. Okay, now we're going to do a little bit of notation. We're going to plug this back into the original, right? But what we want here is a function, all right? So we're going to say this is W of t equal to, the initial amount was 2, e to the 0.2798 t. Yes. So your final answer should be third decimal place. For the k's, we like to go a little more just to, give us some less margin of error. Okay. So that's WT. That's the equation. This is the function W as a function of time, right? This is W as a function of time. What I want is how much the puppy will weigh when it's 3 months old. So that is W of 3, 0.2798 times 3. So W of 3 is 4.630 pounds. So it's important to get our notation straight like this for a couple of reasons. Very rarely are you going to be working with just one function at a time. So when you label things properly, it helps you differentiate and keep track of all the different functions. This is W of t, this is S of t, this is blah, blah, blah. Also, many times in calculus, it's not just about the answer, it's about, hey, so what does this quantity represent? And you have to say W of t or W of 3 is the amount that the puppy will weigh when it is 3 months old. Like, you have to say it out. So and having the proper labeling also helps you determine what it is that you have, right? Okay. Ready for another one?
The last page.
Yeah. Yeah.
We're doing 2 days.
Right, because we have word problems for homework, and we know how that gets.
So it's one of those extra days allotted to go over stuff.
Right. Yep.
I was a little scared. I turned the page and I'm oh.
I know, right? And you thought pre-time. Okay, so yes, this is a problem on having to do with an epidemic. Okay, so here's the thing. Nothing. Okay. Exponential growth and decay are the models for how viruses, pandemics, epidemics, spread, right? And my goodness, have we seen exponential graphs over the 2 years, you know, like just splattered all over the TV screens, right?
So
Yeah.
you're telling me the math teachers plan COVID?
Okay. Okay, so, you know, these are like, they really do model what we're doing really well. So, you know, like this is a problem. These are like classic examples that we do in AP Calc, you know, for years and years and years. And like, we even did it over Zoom last year, you know, when we were like really in the thick of it.
So got more of a kick then.
Okay, so during a certain epidemic, the number of people that are infected at any time increases at a rate proportional to the number of people that are infected. Do you see that? The magic words. So if we're going to use, so here's where you decide what variables you're going to use. I want to use capital P of T for people, population, right? So dP dt is equal to K times P. Okay, that's how it works. If 1,000 people are infected when the epidemic is first discovered, so at T equals 0, and 1,200 at 7 days later at T equals 7, how many people will be infected 12 days after the epidemic is first discovered? So, same sort of situation. This implies P equals P naught e to the KT. So, final 1,200 equals initial 1,000 e to the K times 7. Dividing, we get 1.2 is equal to e to the 7K. ln of 1.2 is 7K. So K is ln of 1.2 over 7. This problem could easily be part A or B or C of an FRQ, okay? And then like part B would be, okay, now do a slope field for this, you know, whatever. You know what I mean? Like, so that's how. No. So now P of T is P naught e to the KT. What we want is P of 12 is 1,000 e to the 0.026 times 12. Oh yeah, so K is about 0.026. So P of 12 is roughly 1,367 people, I believe. But I also want to show you to really get the most accurate answer here, because sometimes it does make a difference. I want you to use the stored feature in your calculator, right?
You always round down for people.
No, so you round as you would. Yeah, you round as you would, because it's an average, sort of like it's an estimate, right? So, huh? In science?
No, in stats.
To where?
In stats,
Right, what did they say? To
round up.
Round up? Okay, yeah, so in AP Calc, we just round to, right, above 5, you round up. So here, okay, so here's what we're going to have. We're going to have ln 1.2 over 7. So it's about this, right? And I write this just so I have something to insert into my formula. Then I do that. But then when I want to calculate the final answer, it's going to be 1,000. Sorry. That's not what I wanted. E to the power of, okay, here, put in the answer. And you can do it in 2 ways. You can either say control answer, or you could also go up here and do that. I know, times 12.
Wait, what did you put?
Okay. So here, so do you see how it's like 1,367 people? So suppose now, okay, so now you've done this, right? So this is kind of cool. So now you've done like a couple of calculations. And then suppose now you wanted to do like ln of 1.2 over 7, you know, plus some other value, right? You could still do it. You could go up, 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 take this, enter, plus like 36, you know, So you could still reuse old values. You could just go and click on them and reuse them. Okay?
That's something we should be teaching freshmen.
Super cool.